Are we gonna have to remember that binomial formula and manipulate it in the way you showed in the example ourselves on a quiz or exam?
Well, I mean, yes and no. I mean, I definitely want you to know the binomial theorem. I mean, that's something that we talked about before.
Mhm.
Um, it, I mean, no, in the sense that I don't necessarily expect you to be able to like start at the beginning and be able to handle that. Um, but I do want you to know that like the sum of the binomial coefficients, which is just the chooses, right, of a particular
Mhm.
size, that's just 2 to the size that you're working with.
Okay.
We ended up working, that's what we ended up using in the end to make that work out.
So just know what we ended up with from the binomial formula, that the sum of
Yeah,
choose
yeah.
x of, say, y choose x is 2 to the y.
Right.
Just know
The
that.
sum of all of them is just right. The sum of all of the n choose k's is just 2 to the n.
Okay.
Add them all together. That's an important fact. And the binomial theorem itself is important. So that's a good thing to have in your back pocket.
Okay. Thank you.
Yeah, I mean that was sort of an intense manipulation. Hopefully, it made sense. I mean, like if you see a bunch of discrete steps of how to do it, but kind of seeing through to the end of that is tricky. But in the end, the answer ends up being fairly intuitive, doesn't it? That the expected number of heads was just half the number of flips. Yeah. So, and we'll see a more general version of that later. But that one was to prepare us for what I'm going to do next. What else? Other questions? It's a good question.
Just out of curiosity, so are they making all the profs like not come in to their offices, or how's that working?
Uh, that's a little unclear. I think that we may have the flexibility to go in if we want, because we're technically like a distance learning institution right now, and and I think that gives us some leeway in terms of being able to go into the office. Um, I mean, I went in there today just briefly to grab some things, and like everybody was, well, not everybody, but a lot of people were there. So I'm not sure if people are going to just keep going in or not. But there was an email that went out that just said, "Yeah, we don't really know what all of this means yet, so we're just going to sort that out over the next couple days." I don't think the order goes into effect until like midnight tonight, anyways, in Ohio. Um, I know that some of you guys are in different states that have already instituted a lockdown, but yeah, yeah, should be interesting, but we'll sort it out.
I didn't think they'd still have everyone coming in to get their stuff like after the lockdown started, but I guess they are.
Oh, you mean like moving out? Oh, huh. I hadn't thought about that. That's interesting. Yeah, I don't know. Man, I hope you guys are able to get that worked out. That seems sort of complicated.
Yeah, I'm
Yeah.
I'm supposed to go on Tuesday, and it takes place at midnight tonight, I think. And then, I mean, they told me I'm still good to go on Tuesday, so I don't know.
Okay. Yeah. I guess if you have a good enough reason, you're not going to get thrown in jail or fined or something. I don't know if that would happen anyways, but yeah. Well, other questions? Anything else?
I'm only like halfway through the lecture for today, so I haven't watched all of that. But um, you said we're gonna have an exam? Is it on Wednesday or more info on Wednesday? How is that gonna work?
Well, I still need to sort that out, but I mean, it's going to be a take-home test, uh, and I just need to sort out the details of what that's going to look like. So, like, what the time constraints would be. Um, I'm not so much concerned about the amount of time you spend working on it as I am like, okay, how many days do I give you to have it, and then actually before I actually require you to turn it in. So I, I'll have more clarity on that on Wednesday, or probably even by tomorrow, just so you know.
So, like with all the stuff we've been doing recently, like there haven't been any other like homework problems. So, like, would problems on the test be like similar to the ones we worked through, or will they use
Yeah.
it?
So,
Or
so the test would be up through the end of that probability fundamentals um, stuff. So the last slide presentation, um, the stuff I started for today's lecture, I wouldn't put that on the exam. But any problems of the sort that I put on those slides would be fair game. So I've kind of been holding you accountable for those by giving you quizzes on those. That's the sort of thing I would hold you responsible for, like being able to do those kinds of problems. So yeah. And I think, I mean, like I did, if you watched the class session, I think, was that last Friday when I was doing the thing with Bayes' theorem and the pregnancy test thingy or
Yeah.
something?
yeah, that was Friday.
Yeah. So, I mean, something like that. I mean, that's not all that different from the device and locator, or from the disappearing plane locator problem that we were doing. But I mean, I wouldn't anticipate any like super complicated applications of Bayes' theorem. Those kind where you basically just have two sets making up the whole sample space. Those are the most important in applying Bayes' theorem. So those are the ones I would be the most familiar with, for sure.
And is the test going to include like cryptography?
Yeah, cryptography would be included on that. Yes. Because the last test just went up through like induction or something, right? The last test just went up through induction, like strong induction. So we started number theory after that. So it would be all the number theory stuff, which includes cryptography, counting, like the enumeration stuff and the probability stuff. So those would be the topics to make sure you're comfortable with, for sure. But again, it's going to be I think it'll be like open book, open notes, because I don't really want to have to govern all of that. So I would just write the test in such a way that makes sense. And I would probably give you somewhere in the vicinity of like a week to turn it in or something. That's kind of what I'm thinking off the top of my head. Now, some of those parameters might change ever so slightly, but that's what I would anticipate for the most part. All right. Other questions?
On Friday's lecture, you said that a lot of people end up like misusing Bayes' theorem and they get messed up on that. Just out of curiosity, like what are some common ways that people mess that up, or where do they go wrong in that?
Well, I think I kind of alluded to that when I was. Oh man, sorry guys. I think I kind of alluded to that when I was saying that, like, there was an HIV test I think at the very end I said something about an HIV test. So HIV test, what they did is they administered the test to people that had the disease, and that thing was coming back hopefully positive a fair amount of the time. Does that make sense? So it was given that the person had the disease, and the probability of positive given that they had the disease should be very high. And similarly, they gave it to people that they knew did not have the disease, and what the probability that is negative should be very high given that they don't have the disease. Does that make sense?
Yeah.
Then what they did is they said, oh yeah, these seem like they're high enough, let's get this thing to market. They kind of rushed it to market. It's kind of like this. Did you know that the FDA has been having all these problems with the coronavirus tests? So like they take a long time. Some of them are giving a lot of false positives. There's a lot of false negatives also. There's just been a lot of issues. And so what ends up happening is they'll test it and they'll think, oh, that seems reasonably high for true positives and true negatives. But then they don't actually go through the process of flipping it around in Bayes' theorem. And in that pregnancy example, even though the true positives were like 95% and the true negatives were like 99%, what did we discover the probability of being pregnant given that the test was positive ended up being? You guys remember?
80%.
Yeah, it was like 80%. It was way lower. And in the case of the HIV, positive and negative test, they rushed the thing to market without really kind of thinking through the implications of Bayes' theorem. And then they had a bunch of people testing positive, and literally, I'm not kidding you, like 50% of the people that were testing positive actually had the disease. So I mean, it was just horrible. So they hadn't really taken into account what happens when you flip the conditioning around. Does that kind of make sense, Aaron?
Yeah, it does.
That's why I was kind of stressing those true positives and true negatives need to be extraordinarily high.
The main problem is actually people don't use Bayes' theorem.
Yeah. So those true positives and true negatives to be extraordinarily high in order to ensure that when you flip that thing around, that the Bayes' theorem still is going to give you a high probability once you flip that thing around. So I have a little chat window question. Says, can you clarify how rational numbers are considered to be discrete data? Now, I mentioned that discrete data is data that is listable. Yeah? Discrete data is data that is listable. And sometimes it's helpful to think that it's like, that there are gaps between the numbers, just like there's gaps between like the number 1 and 2, right? You can almost, like with discrete data, you can discern little gaps between the things. But one way to make that rigorous is to say, I can actually list the data rigorously. I can write them all down systematically in such a way that I am guaranteed to eventually get to every number. And Ryan Albrecht is asking me, how are the rational numbers listable? How is that possible? Well, here, tell me if you can see this. I was having all kinds of trouble earlier, but I'm gonna see if this works. Tell me, does this work? Hang on. You see that?
Yeah.
Okay. Oops, sorry. I was horsing around with this. Oh, wait. Clear page. Okay. So watch this. What is a rational number? Is a ratio of integers, right? It's just a ratio of integers. So check this out. If I go, if I first write down all of the rational numbers that have, well, first of all, you have 0, right? 0 is kind of stupid. Yeah. But then, okay, what about all the ones that have 1 in the denominator? Well, there's plus 1 over 1. There's minus 1 over 1. There's plus 2 over 1. There's minus 2 over 1. There's 3 over 1 and minus 3 over 1. And then I just keep writing it in this row on forever. Okay? But then, what about all the ones that have a 2 in the denominator? So like this, plus 1 over 2, negative 1 over 2, 2 over 2, negative 2 over 2, 3 over 2, negative 3 over 2, and on it goes forever. What would the next row be? Do you see what I'm systematically doing? What would the next row be that I would write down?
With the 3 in the denominator?
3, right. So it'd be 1/3, negative 1/3, 2/3, negative 2/3, 3/3, negative 3/3. Do you see that every single rational number is gonna be, and by the way, we just keep going forever in this way. Do you see that every single rational number is gonna be in this like infinite matrix that I just wrote down? Yeah. Well, how would I actually list the rational numbers then? Well, what you can do is you can snake through this. So I can kind of go, I snake through it like this. Okay. And this tells me a way to list. If I kind of snake through this thing, it tells me a way to list all of the rational numbers eventually. So like, what would be the first number that I would write down if I just follow this snake?
1 or 0?
Well, 0. I would first write down 0. What would be the next number in the list?
1.
What would be the next number in the list?
1/2.
Yeah. Next number?
Negative
-1.
Negative 1. What would be the next number?
2.
And then?
Negative 1/2.
And then a third. And do you see how this is just going to go on forever? But in this way, I mean, there isn't a single rational number that you could tell me that I wouldn't be able to eventually arrive at. Does that make sense? Every single rational number, I don't care how clever it was, negative 429 over 7,324. Well, eventually we will get there. Does that make sense? In sort of listing in this way. So it's kind of interesting. Okay. How do I get out of here? Oh. Okay. How do I get it? Hide, stop. Okay. Okay, stop participant sharing. Okay, there we go. And I just kicked myself out. That's great. Okay. Oh well. All right, so that was kind of an interesting thing. Hopefully that makes sense. That's sort of a famous way to systematically write down all the rational numbers. So anything that can be listed like that is considered to be discrete. Anything that's continuous is not going to be listable. Any data that's continuous will not be listable. That's interesting stuff. So what that actually shows, and this might not be clear to you right now, but it actually shows that there's more than one level of infinity. there's kind of this listable level of infinity, like I can list stuff. And then there's this like higher level of infinity that apparently is not possible to list. It's so numerous in terms of its infinitude that it's not possible to actually list it. And that's the nature of continuous data. So yeah.
So you said, like you said, all the numbers between 0 and 1 would be continuous, right?
That's continuous data, yes.
So that just means there's no way to write out every number between 0 and 1?
Yeah, that means that there's no way to write out every number. Yeah.
But there's, okay, yeah.
So you want to see why that's true?
Yeah, sure.
Okay, so let me do it. I accidentally booted myself out of here, so I got to get myself back in now. Let's see, 984-460. 8453. Okay. There I am. Okay, here it comes. Okay, so watch this. Why are the numbers between 0 and 1 not listable? Well, suppose they were. So if the numbers between 0 and 1 were listable, then we could make a list. Then we could list them. Okay, so this is basically a proof by contradiction. You sort of assume for the moment that it was possible, and then you show that something goes wrong. Okay, so like maybe the first thing in the list is like 0.21370, etc. Maybe the next thing in the list is 0. So this guy's first. This guy is second. Okay. 0. I don't know, 1, 3, 5, 0, 2, etc. The next one is 0.99704, etc. Okay. And then this list is going to go on forever. Okay. So I claim, or suppose Aaron made this list. Okay, and Aaron says every number is in this list, and I would say, oh yeah, well, look at this. Look at this entry, the second entry of the second entry of the second number, the third entry of the third number, etc. Like you kind of go down the diagonal like that. I claim that the number 0. Okay, I just have to pick something different from 2. Give me a number different from 2.
4.
4. Now give me a number different from 3.
5.
Okay, now give me a number different from 7.
6.
And do you see that in this way? So is this number in the list?
I don't know.
No.
Well, is it the first number?
No,
Why can't it be the first number?
because the first number starts with a 2.
Yeah. Is it the second number?
No,
Why can't it be the second number?
because the second number has a 3 at the second place.
Yeah, right. So it's different in the second position. It can't be the third number because it's different in the third position.
Oh,
It can't be the fourth number because it's different in the fourth position. So this differs in the ith position from number I, right? So from the ith number. So is this thing in the list?
No.
No, this thing is not in the list. So you say, oh, well, so what? Just slap it onto the front of the list. But then what would I be able to do again?
Same thing.
Same thing. I would be able to do the same thing. And there's no way that you would ever be able to write a list that would get everything. I could just keep heaping another number in there and say, well, that one's not on there. Whereas before I was able to actually list everything. This is actually called Cantor's diagonalization argument. So this argument comes from Cantor. Georg Cantor. Georg Cantor is the guy that did that. Okay. So that's a proof by contradiction. You assume and they are listable, and you show that there's no way that your list could possibly ever be complete. So I think that's a pretty cool argument. Okay.
This might be kind of a dumb question, but what's the difference between probability and statistics?
Hang on, I'm trying. People are texting my stinking iPad like crazy here. So sorry. Hang on. Okay, there we go. So the difference between probability and statistics is, so probability is like is a really rigorous science. I mean, all of it is theoretical. You know what I'm saying? Like it's all like theoretical. But in practice, if I go out and I flip a coin 1 trillion times, certain events either happen or they don't. Do you know what I mean? It's like there's a probability that something happens, but then it either happens or it doesn't. And if I keep repeating that experiment some number of times, in the long run, I'm going to see the number of times that event happens over the total number of times. That fraction is going to be close to the theoretical probability, right? So the statistics side is kind of that dirty science where I'm actually putting the probability into practice and seeing what happens. I'm gathering data and I'm actually seeing that the probability theory undergirding it is kind of playing out. Does that make sense? So probability is like the theoretical rock solid science that undergirds like the dirty collection of data that needs to be analyzed.
Okay.
So that's the difference between probability and statistics. Statistics are, statistics are uncertain, whereas probability is more certain. I mean, you at least are able to say with certitude, here is the probability that this particular thing happens or something like that, okay? So probability is like more theoretical. Statistics is more like applied probability. Okay, you're kind of applying probability to the collection of data and analyzing of it.
Okay.
So we'll see why all of this stuff is going to be helpful to that end pretty soon. What else? Anything else? Some good questions.
Going back to the infinite number thing, were you saying that basically there's more numbers between 0 and 1 than there are like cardinal numbers?
There are more numbers between 0 and 1 than there are integers. And there are more numbers between 0 and 1 than there are rational numbers, for instance. And here's what's weird. The number of integers is the same as the number of rational numbers, even though the integers are rational numbers. Does that make sense? Both of those sets are listable. I can list the integers, but I can also list the rational numbers. And therefore I can put them in one-to-one correspondence with each other. Because I can write the list side by side and just say, look, they line up one by one like this. So that means that the rational numbers and the integers actually have the exact same size as infinite sets. But the numbers between 0 and 1, the real numbers between 0 and 1, that is something else. That's a crazy huge set. Way bigger than those listable things. And by the way, there's not just like 2 levels of infinity. It turns out there's like infinitely many levels of infinity. You can just keep building bigger and bigger and bigger sets by doing some crazy stuff with them. So, yeah.
Is there any application for that with like different levels of infinity?
Yeah. So, yeah, I mean, it's more like in the foundations of mathematics. All this stuff about infinity kind of forced mathematicians to get their ducks in a row when it came to actually writing down how you go about proving stuff and what sorts of things you need to assume in order to prove things. So actually one of the biggest results of the 20th century early on was there. You guys ever heard of a guy named Kurt Gödel? G-O with an umlaut, D-E-L. He proved something called the incompleteness theorem, which basically says, and this is actually one of the most important theorems in all of foundational mathematics. It basically says that if you are working in a mathematical system that is complicated enough to have the integers in it. By the way, that's not very complicated. The integers, that's like what we use all the time, right? If you're working in a mathematical system that's complicated enough to have the integers in it, then you are bound to come across statements, mathematical statements about that system that are undecidable. Undecidable, which means you can't prove them and you can't disprove them. And that rocked the mathematical community because they thought that mathematics was impervious to those kinds of things. Like everything was either true or false, and you just proved it to be true or proved it to be false. But what Gödel said was, no, you're going to run into some statements that are undecidable, and you basically either have to accept them on faith or reject them on faith in mathematics, which is totally weird. Okay. So Josh sent a little YouTube video. Is that talking about Gödel's incompleteness theorem or something, Josh?
It's about different levels of infinity.
Oh, yeah. Yeah, so Gödel's incompleteness theorem really blew the lid off of things. By the way, that guy I mentioned, Cantor, remember I said Cantor was the one who gave the diagonalization argument? He got obsessed with the following question. He was like, okay, I showed that there's the listable infinity and there's the unlistable infinity. There's the listable in infinity and there's the unlistable infinity. But is there any size of infinity that's between those two? Does that make sense? Is there some set that has size that's like strictly between the listable infinity and the unlistable one? And he actually put himself in the loony bin literally trying to figure that out, and died at the turn of the 20th century having not proved it. And then Gödel proved the incompleteness theorem. And then in 1969, a logician by the name of Paul Helmich actually proved that Cantor's statement, or Cantor's problem that he was working on, was an undecidable statement. So he was either going to have to accept it on blind faith or reject it on blind faith. Rachel's over here saying, how did he try to prove that theorem? Which theorem? The incompleteness theorem, Judy? Is that what you're asking about? Or Rachel? Sorry. Rachel. The incompleteness theorem? Yeah. He had to invent some new proof techniques. in the realm of mathematical logic. He used a technique in mathematical logic called forcing. So it was kind of tricky stuff for sure. So listable, unlistable, infinity, all that stuff is, man, that's some interesting mathematics for sure. Lots of mathematical blood has been spilt on those topics. All right, what else? What else?
Is there anything like that's been going on like recently in the past, I don't know, like a year in mathematics? Like I never hear about any groundbreaking news or anything. Like, has anything been discovered or anything cool like that?
Yeah, there's always new mathematics being developed. Yeah, for sure. I mean, there's always these prized problems out there that people are trying to chase down. I don't know, like you guys are in computer science, the K-satisfiability question is a big one. If somebody was able to solve that, they would be the most famous mathematician of all time, because it solves a lot of other things. There's another problem called the traveling salesman problem that incremental progress is always being made on. But there's also a lot of other areas in mathematics where people are just constantly making new discoveries. I mean, to go get a PhD in mathematics, you actually have to do brand new mathematics. In fact, if you get a PhD in any field, that's basically what you've done, is you've contributed something new to the field. So there's always new math being developed, which sounds kind of weird because math is so ancient, right? But there's always new math being done for sure.
What did you do for your PhD?
I looked at, we talked about permutations, right? So I looked at permutations, and I looked at a sorting algorithm on permutations and asked the question, if I take two unordered lists of data and I start sorting the one, what's the probability that in the process of sorting the one that I will encounter the other, and then I would be able to sort them side by side one another. So it's like the same data in a list, both of them out of order, and I start sorting the one, and I want to know what's the probability that I will encounter the other so that I can then save time and sort them side by side from that point on. That's called the Baruha ordering on permutations. And it was a problem in combinatorics and probability. And what I showed is that almost never happens, that you might as well just sort the thing without worrying about whether you're going to run into the other one. So that's what I did. And everything else I've done has been something kind of like that, something that has to do with that. But yeah, that's the sort of thing mathematicians think about. Well, hey, good questions. Above and beyond the call of duty. Anything else? Yeah, if you go, I mean, if you're really genuinely interested, you could go Google, you could Google my name, and there'll be some papers that come up, and you could see the sort of thing that I've looked at. It usually has to do with permutations though. So you can at least read the abstract and see what it says. But yeah. What else? Anything else? Anything else? Pretty soon I will go and actually put a homework set from this new Alowski Dean material up in Canvas. so you can start working through questions in that book. Okay. I put the PDF file in Canvas for your convenience. Did I put the latest slide presentation in Canvas? Did I put the PowerPoints for chapter 4 of Olowski Dean? I don't know. I can't remember if I did or not. If not, I'll do that as well.
I'm looking at it right now. I don't think they're on there.
Okay. Well, I'll put those in there. The stuff that, or the slides that I was using to do the lecture from today. I'll put that up there. Okay. Hopefully this is working all right. Is YouTube working okay? Apparently Ensemble has been giving some students some fits. We got some communication about that. You know, maybe not you guys, but some students have been having trouble. It's kind of glitchy. You know, the streaming quality isn't great. So I think staying in YouTube is a good call, is a good move at this point. So I'll just keep putting those up in there and just alerting you to the fact that there's new things there when there are new things. Okay? Okay. Any other questions? All right. Let's call it a day. Take care, everyone.
Thank you.
Thank you, Dr. Hammett. See you.
Yep.
Thank you.
Yeah.